Okay, so sunlight, as we saw in lab, is a complete spectrum of the wavelengths. When we saw this in lab, we saw that it looked like a blurry kind of like you saw all the colors, right? It looked like through the prism we were looking at the complete spectrum. When we looked at the classroom light, that looked like a line spectrum, right? There's a lot of little lines in there. So that was the difference between those two there. The spectroscope we used in lab is a prism, and it can be used to separate the wavelengths. So even though we see this as white light, when you use a prism in it, it'll divide it up into all the different colors. Okay. And then naturally you'll see some prisms like rainbows and sunsets, which are splitting up the light into their representative wavelengths. All right, so visible light, what's the longest wavelength? What color? Red. Yeah, good, so that's red. And then what's the shortest wavelength? Good, that would be our violet. And then to remember the order, it's Roy G. Biv, right? Exactly. All right, cool. Okay, so here you can see violet has a shorter wavelength, red light has a longer wavelength. Which one would have more energy? Violet. Yeah, the violet, right? Which one has a higher frequency? Violet. Violet, yeah, exactly. So you have violet, higher frequency and higher energy. Good. Okay. So all elements emit light when electricity is passed through them. An atom gains energy, so the electron becomes excited, and then it moves to a higher energy level. Then the electrons jump back down to the ground state, which releases energy as light. And then this is the atomic emission spectrum of that element. So in lab, when we looked at hydrogen, what was happening was hydrogen was in that glass tube. We zapped it with electricity, which means the hydrogen atoms all absorbed that energy, all right? So when we look at hydrogen, hydrogen has this little nucleus, and then it has an electron, all right? When you zap it with electricity, that's putting energy into it. That electron that's on the first energy level gets excited, and it can jump up to a whole bunch of different energy levels. And there's a lot of hydrogens in that glass tube, so all of them were jumping to different energy levels, all right? So they're getting excited, they're jumping up, and then what happens is the electrons then jump back down, and when they jump back down, that's when light's given off. So we don't see them jumping up, we won't see that. What we'll actually see is when they jump back down to an energy level, that'll give off some kind of energy as light. Sometimes it's visible light, sometimes it's not. They can actually give off UV light, so you can get some UV, you can get IR, it'll give off heat. And if you think about with light bulbs and whatnot, you know that kind of happens, especially with the older light bulbs, that they'll get real hot, right? When you turn them on, well, that's because they're not that efficient. They're giving off a lot of heat as well as light. What do you notice about LED light bulbs? They usually as hot? No, usually when you turn them on, you can touch them, right? They don't burn you. That's because most of their energy being given off is in the visible spectrum. So they're not wasting a lot of energy giving off heat. So that's why they actually are more efficient, because they're not giving off heat, all right? Okay, does that make sense? Absorbs energy, jumps up, we don't see that, but then we'll see it when it jumps back down, okay? Now, when it jumps back down, we'll see the average of all of these. We'll see that as what you saw in the spectroscope in lab before you put on the actual spectroscope to divide the prism, to use it as a prism to split it up. When you use the prism, then you can actually see when it's jumping to different energy levels. Okay, so each element has its unique emission spectrum. We looked at hydrogen, helium, and mercury, and they all looked different, all right? The light given off by your element is specific to that element. It's called the emission spectrum for that element. It's kind of like its fingerprint, so you can detect what element you're looking at by zapping it with electricity and doing this technique to see what it looks like. And then we used a prism to see it, and that's the best way to do it. All right. So in lab we had our lamp. It was hydrogen. And then we had that light shine through our little spectroscope here. In the spectroscope, there was a prism. That prism split up the light into all the different wavelengths. And then when you looked at it, you would see this band. And most of you guys were able to see the red, the teal, And then the blue, I don't think anybody was able to see the violet with hydrogen, just because it's hard to really see that one, but technically there is another one on there. If you saw it, that's awesome, but I can't see it. So yeah, 1, 2, and 3. So everybody should have at least seen those 3 when we were looking at hydrogen. All right, cool? Okay, now, when these electrons jump, they're called different things. There's different series. So one of the series is when you have the emission spectrum lines in the UV region, they arise from electrons in the higher than the first energy level returning to the first energy level. So what this means is when those electrons jump back down, so if it's here and it jumps back down to the first energy level, the light that's given off is in the UV range. Okay, so it's giving off UV light. All right, that's what it's called, the Lyman series. All right. And you can see that here. This is an example of a whole bunch of different electrons jumping. So each of these lines represents the energy level. So this is the first energy level, second energy level, third, fourth, fifth. So check this out. If you were an electron and you jumped from somewhere really high up here, you jumped all the way down to the first energy level, you'll see that the wavelength is smaller than if you jump from the second energy level down to the first energy level. This wavelength is bigger, right? So if this wavelength's bigger and this one's smaller, which one of these has more energy or gives off more energy? Yeah, the one on the left, right? The smaller one, right? Because the smaller wavelength, it's going to have more energy, which makes sense that it's jumping further and it's giving off more energy, right? So you have this big jump, it gives off UV light. We can't see it, but you know, it's UV, we could observe it different ways. And then if you do the same thing but jump to the second energy level, then it gives off visible light, and that's called the Balmer series, all right? So if you're up here and you jump down to the second energy level, you would give off violet. And this is still hydrogen, all right? So this is still hydrogen. You can see the lines for hydrogen. So we saw this yesterday. When it jumped from the third down to the second, that's not a lot of energy. That's why it came up red, because red doesn't have a lot of energy. When it jumped really far, it came up violet, because that is a lot of energy. All right, does that make sense? Okay. Also, what would happen is if it jumps to the third energy level, it would give off infrared, so it would give off heat. So if you were to touch the light bulbs yesterday, the spectrum tubes, which again I said don't touch them because you don't want to get your oils on the glass, you would feel that it would give off some heat. All right. So this is what's happening. This happens in all light bulbs. So you'll get all these different things. Now again, if they're filled with hydrogen, you would get this exact same thing. But light bulbs are filled with different elements and whatnot. Like these ones have a lot of mercury in them. So that would give off a different spectrum. Okay. Any questions with any of that? No? Okay. So that's the spectrum. Jumping down. All right. So the Balmer series, the emission spectrum lines in the visible region, and it arises from electrons in the higher than second energy level moving to the second energy level. And again, as you jump down, so if you're on, there's first, second, third. If you jump from the third down to the second, it's going to give off light that you could see. All right, jumping down gives off light. When it jumps up, it doesn't give off light. It's absorbing energy. All right, and it happens really, really fast. So that's why when you flick the light switch, it looks like the lights turn on immediately. But what's happening is you're turning the light switch on. The atoms that are in the light bulbs, they're getting energy. Those electrons are jumping up. We're not seeing anything, but as soon as they jump back down, that's when it gives off light. And it just keeps happening over and over again until you turn off the electricity. And that's why it looks like the light's just constant, right? But you've been in situations where you've seen lights flickering and stuff. That's when it's not working the way that it should. And you'll get that kind of like flickering. Okay, so this is just a review of everything that we just kind of talked about. So hydrogen has one electron. Normally this electron is in its ground state. It's not excited. If you add energy, it gets excited, jumps to a higher energy level, all right? We don't see anything for this, all right? So it's at a higher energy level. It takes a quanta of energy to move from one energy level to another, so a specific amount of energy for it to jump up or jump down. Once the electrons are excited, they lose energy, which emits a certain emission spectrum, and we would see that as visible or UV or IR light. All right, so it would give off this different light. Okay, any questions?